Good morning, class. Good morning. I hope at this moment you have already started practicing with using the tutorial. Okay, have something running in using Fluent and enjoy the run so far. Okay. Let me know if you have any difficulty. Okay, I think that the two tutorial seems good to me, especially the second one, the detailed one. Okay, so let me talk about project one today. Okay, right now. Okay, I will post the a detailed description, a PDF description online. I'd like to talk to you about it. Uh, Give you some explanation. Okay, hopefully everybody is clear of what you are going to do. Okay, the case you will simulate, it will be similar to the tutorial case. Okay, instead of a rectangular shape of material, this time you will do a square shape of material, 0.8 meter by 0.8 meter. Okay, that's the size. It's a 2D simulation still. Okay, but I would like to mention 2D is not really, the third dimension is non-existing. Okay, 2D, what 2D means? The 2D means the third dimension is infinitely long. Okay, so you don't have any change along the third dimension. Okay, think about this is a long rod, square shape. Okay, very, very long. So any cross section you will see the same temperature distribution. Since it's long enough in the third dimension, any cross section will be the same. Okay, so you will have a temperature distribution inside the material, inside the slides, but each slides will look the same. So if that's the situation, we can assume you use 2D simulation because you don't need the third dimension because it's long, very, very long, and it will be the same along the third dimension. Okay, so that's what 2D simulation. So the boundary condition, you will have T1 and T2 on top and the right boundary. It's up to you. You decide the two temperatures. Okay, and the left side is the surface is exposed to the ambient air. Okay, so you will have a air temperature 300 degree K, which is the room temperature, right? You need to do some research about the heat transfer coefficient for the air at the room temperature. You decide a H value. Okay, put those things in the report. Okay, by the way, after you do the project, you need to submit a report. I already posted a very simple report format. Please follow that. It will be similar to my lab report, fluids lab or heat transfer lab. Maybe some of you already did my lab, so you're already familiar. Okay. Okay, so the bottom boundary is the insulated boundary. So now you know the insulated boundary, you have zero heat flux. Okay, that's the insulated boundary condition. Okay, and so left is convection condition. You need to input the ambient temperature as well as a heat transfer coefficient into the fluent. Okay. Okay, you will going to run 3 cases, at least 3. You will actually run 6 cases, 3 cases for steady state and 3 cases for transient simulation. Okay, you would make 4x4 mesh, 8x8 mesh, and a 16x16 mesh. I say mesh actually the same as grid, right? 4x4 means there's 4 grid cells along each direction, each dimension. 4 grid cells, so 4 blocks, right? Okay, so in that sense, you will have 5 grid points, actually, cross sections, 5 corner points. Okay, so 4x4 means the number of the grid cells. Okay, same thing, 8x8 and a 16x16. Okay, the reason I want you to test the 3 grid levels, that's the thing I want to talk about right now, very important. You know, as we discussed in the lecture, the first lecture, okay, your accuracy is dictated by the grid resolution, right? The finer grid you have, the more accurate result you have, because you do approximation. You assume between two adjacent grids, they are linear solution. You use linear equations, but actually reality is not linear. So if it's grid spacing is too big, you have more errors. Okay, so always as a CFD engineer, you want to do a simulation. You want to know what grid size is appropriate, because you don't want to do too many grids, because it will slow down your calculation, slow down your simulation, because every equation, so all the equation will need to be calculated on every grid point. So sometimes it will be really costly, really time consuming. So you don't want to do too many, but you don't want it to be too less, because it's not accurate. Okay, so the way we decide the grid number to be used is actually to compare to itself. Okay, if you compare 4x4 to 8x8, if the results are different, okay, if there's a noticeable difference, that means at least 4x4 is not good. It doesn't mean 8x8 is good, but it at least means 4x4 is not good. You know what? The truth, there's only one truth, right? For this physical problem, there's only one temperature distribution inside. Every grid point you will have a temperature, but the reality, the truth is only one correct temperature. Okay, one correct set of results. But if your results are different between 4x4 and 8x8, then at least one of them is wrong. Do you see my logic? Okay, it doesn't mean 8x8 is correct, but at least it means 4x4 is wrong. Okay, the same logic. Now you don't know if 8x8 is correct or not. At least you can get rid of 4x4. Okay, now you compare 8x8 to 16x16. Okay, if they are still different, that means 8x8 is wrong too. But if they are the same, that means if you refine the mesh to 16x16, the result doesn't change. So you don't need to waste your effort to do 16x16. 8x8 is good. So at least when you reach, that's called grid convergence. If you have two sets of grid, it produce the same result, the chance is likely that the result probably is correct. And you refine it to 32x32, it won't give you any differences. That means you already reach the grid convergence. So that's the logic behind it. So every problems, if you real time you do a problem for a real project, you have to do that too, to determine which grid size is appropriate. Okay, nobody can tell you. There's no theory, you know, what problem is what grid size. You have to test it to determine yourself. Okay, so that's also the process what we're gonna go through for the first project. Okay, that makes sense. Okay, so the required result in your report. I think you already run the result. You probably run the steady state case. Okay, so the steady state means, you know, just like thermodynamics, you predict the ending state if there's a steady state. Some result doesn't have a steady state. Okay, some result have. Like this problem, it definitely has a steady state result, because if you doing real experiment, you test it for long enough, it will reach to a stable condition, right? The temperature won't keep changing, won't keep increasing. It will be steady state, right? Eventually. So for the steady state run, if you select the steady state in the setup, then it won't tell you the information in between from the beginning to the steady state we will reach. It just directly predict at the end state, okay, what the result will look like. So in the steady state case, I want you to produce a couple of things. The first is to plot the convergence history, screenshot. When you run, now you know on the screen, it shows a plot, right? That's a residual. Residual means the relative error comparing to the last iteration, the current iteration comparing to the previous iteration. You know, when you run the steady state simulation, you need to do iteration, right? You run like 7, 8, and 9 iterations. So every iterations in the Fluent compare the whole result in the domain, the entire result in the domain, comparing to the previous iteration result. Okay, you can calculate a maximum relative error inside the domain on every point. Okay, so that residual is the maximum relative errors comparing to the previous times. So you know when the relative error reach to 0, that means the result is converged. You add more iterations, it won't change, right? There are no relative errors. So then we say it converged. So it takes several times, several iterations for the result to reach converge. So that's what Fluent do. So on the screen you have a convergence history. Please screenshot it and put it on your report to prove to me that your steady state result reach the convergence. Okay. Yeah, by the way, the Fluent is doing actually solving that differential equation, right? The heat transfer problem, initially the general equation is the differential equation. So it uses the linear algebra approximate the differential equation. So on every grid point, it will calculate based on the boundary condition, right? When you solve a differential equation, you know you need the boundary condition. The result is directly propagated to the domain from the boundary, right? So the boundary condition dictates actually the result. That's the same thing. You need to specify boundary conditions in order to get the temperature result inside the domain, right? That's the process. I think some students ask the question. Okay, so number 2, I need on your report is plot the temperature contours for all 3 cases. Sure, you will now you know how to see the temperature contours, right? So just screenshot it and do some cut and paste. You know, do some. Maybe you can use a software to like a Paint to just cut the contour down and copy and paste it to your Word report, right? So compare the 3 results, okay, for the temperature. That's for the steady state, very easy, not much to do. So for the unsteady case, you will spend a lot more times on the unsteady simulation. So you will have 3 unsteady cases too, right? Total 6 cases you're gonna run. 3 unsteady and 3 steadies. Unsteady, I want you to compare the center temperature history. So for unsteady simulation, the time information will be implemented. So you, for example, you will take maybe 25 seconds to reach steady state. So from time 0 to time 25 seconds, all the informations, how the temperature evolve, how the temperature change by time, it will be calculated. So you will specify a time step. So every second or every half a second, depending on the time step you select. So it will calculate information at end of 1 second, for example. It will calculate the information temperature at the end of 2 seconds. Every second, it will calculate the information. So you will have all the how to say, all the middle informations, okay, all the information in between the starting and the end. So I want you to choose the temperature, center temperature of this domain. I want you to display that temperature. I want you to plot the temperature history. So you can now. I think in the handouts in the tutorial, you know how to place a monitor, right? Monitor just like a sensor. When you do the actually physical experiment, you place a sensor in the center of the domain, right? That's what the monitor do. So the sensor will record the temperature from time 0 to the end of the experiment. Okay, so it record all the time the temperature information. So you can write out the monitor data into a file, okay, into a text file, and then use Excel to plot the temperature history. So you have 3 temperature histories on the center, right, for the 3 simulations. I want you to place all the 3 curves, 3 temperature history into one plot using Excel. Then you can compare, okay? You can compare to see the difference in the result. because center temperature is the furthest to the boundaries. That's the last point to reach to correct solution. So if that temperature, so the temperature is very sensitive, and it's the last temperature, last location to reach the steady state result. So that's why I choose this point for you to compare. So the purpose of that comparison for the time history on the center is to decide the grid size. Now, as I said before, if A by A is close to 16 by 16, but 4 by 4 is far away from the A by A and the 16 by 16, that means the 4 by 4, the grid size is too coarse. It's not good, right? So that means A by A is appropriate because it's better than 4 by 4, and if you keep refining it to 16 by 16, the result won't change. So there's no need to further refine. So that's the logic we want to see, okay? We want to prove. So this is number 3. I want you to plot the 3 curves in one plot and compare to decide the grid size. So after you decide the grid size, you can get rid of the other 2 cases, 4 by 4 and 16 by 16. If you decide A by A is good, then the other 2, you can just simply use A by A to produce number 4, determine the time stepped, the time required to reach the steady state condition. So you can use the time history plot, because at the beginning the temperature is not right until long enough, then the temperature reach to a stable temperature which doesn't change anymore. So that's the time you required for the whole material to reach a stable condition. Decided from looking at that plot, you can determine how long it takes. Okay, so this is number 4, determine the times required to reach steady state conditions. So number 5 is very important. I want you to plot some intermediate results. Okay, so for example, you run 25 seconds. I want you to stop the run at 1 second. Let's see what's the domain look like, what's the temperature look like. Then 5 seconds, what's the domain look like, and 10 seconds. So the temperature inside the material keep changing, right? It evolves from the initial temperature you specified to the steady temperature at the end. So there's an evolution, right? So I want to show the change of temperature inside the domain with time. So pick at least 4 different times, okay, to plot the contours and to see how the temperature change with time, how the temperature evolve. Okay, so that's number 5. Then overall, in the report, right, I want you to have some discussion of the results, all the results you produce, any discussion, and what are the physics related to it, and what is the error, so on and so forth, those kind of things. We need some discussion, okay? Okay, so I guess that's project 1 description. Okay, so from item 3 to 6, you can use the result from the determine the grid size. Okay, so number 3 is to determine which grid size to use. So then after that, you use determine the grid size result to determine the time, to plot the contours, and do some discussion for the physics. Okay, because that's the best case, right? So your 3 cases, 4 by 4, 8 by 8, 16 by 16, you use the 3 cases to simulate the same problems. It turned out to be the A by A maybe the best one. So you can just simply use that, determine the grid size case, to use that result to do some research, to do some discussion on the physics. Okay. The summation. I think I have detail posted on Moodle. The summation, you need to submit all 6 files. So I think for each case, when you run it, after you run it, you can save 2 files, the case file and the data file. When you write to case and data file, you basically save all the setups in the case file and save all the result you run in the data file. So these are so each run you will have 1 case and 1 data file. So you have 6 runs, right? So you will have 6 case and 6 data files. So I want you to submit all 6 of them. As well as the monitor files, you create monitors for the 3 unsteady state runs, right? You will have 3 monitor files for the center temperatures. So I want you to also submit that along with the report. So totally you will have 10 files to submit. So in Moodle, you can only submit 1 file. So you have to use zip. Please use zip. Don't use .rar. You just use zip format. Zip all 10 files into one package, one .zip package. Then submit that package through Moodle. Okay, so that's the project 1 description. Let me know if you have any questions. Okay, so hope you enjoy this project.